Welcome, everybody. Thank you for coming to my talk. This is composition on tiny embedded systems. And in this case, it's quite literal, as you'll see shortly. So about myself, I'm a firmware architect at Intel, and I work on our client chipset power management. So that's power management for laptops, desktops, the kinds of machines that you would buy. I've been there since 2008, developing software and firmware. But I've only been writing firmware in C++ since 2019. I love template metaprogramming, const-expr, useful abstractions, and I work with Ben Dean and Michael Case at Intel. That little red dot there is the part that we work on. That's the power management controller. It's responsible for turning things on and off, and it's a lot more interesting than I can make it sound, so I won't spend too much time on it. Here's a more recent platform. There's 1 and 2. So that was exciting. This is Meteor Lake. This is coming out, and it's I've seen it in person. It's just really cool packaging technology. But anyways, that's beside the point. This is the tiny system that I'm talking about. It's an ATtiny13A made by Microchip. Microchip bought Atmel. 1,024 bytes of program memory. That's 512 instructions. And that's including the interrupt vector table and everything. Like, that's it. And I've got 64 bytes of data memory. I think it has the same amount of data memory as it does I/O registers and general purpose registers. So I got to be real careful with the stack. It's an 8-bit microcontroller. It's got an internal clock, probably either a ring oscillator or an RC oscillator. But the really cool thing about this, besides being so tiny and cute, is the AVR instruction set for an 8-bit micro is actually fantastic for compilers. It's really well done. And so I'm going to be running some examples and demos here using GCC 12, which is nice. So as you can see, this is a good pairing. I like high-level abstractions, efficient code, template metaprogramming, const-expr execution, and the @tiny can only execute a very little bit of code. So this is the only way it's going to work. So the problem that we have in embedded, and it depends on like how deeply embedded you are and how big is the microcontroller that you're using or the system. It's not always a microcontroller. The problem is this tension between developing firmware that works and is performant given the constraints that we have, but it's also maintainable over time. And we can have multiple teams working on it, and we can take each of their little bits and pieces and we can integrate them, and things should work generally as expected. And then we can develop multiple products based off of that, depending on which components we have. That's what we really want, and that's what I mean when I say compose firmware. So as you can see, we have some very limited capabilities here, and this is going to be fun. In my day job, our microcontroller, our CPU has a lot more power than this, but it's still in the order of kilobytes, not megabytes. So today, we're going to leverage compile time initialization for performance, correctness, and maintainability using the CIB library and C++20. And we're going to build a RGB lighting controller. And it's going to be a very exciting controller that controls a digital LED, but it's going to support logging, which consumers really like. And it's not going to have vacancy or occupancy sensors. Unless it's in a battery, then it'll run out of battery eventually. And it's going to work inside of our constraints. So we're going to see how far we can go, how much we can fit onto this little microcontroller using modern C++ techniques. So here we are. This is our breadboard. This is live. That's me right there. And that's the microcontroller. So it's got 8 pins. You might think it's hardly enough to get anything done, and you'd be completely right. it was very frustrating, and I was working on it up to the very last minute. So this is a breadboard. I want to explain kind of the things here, and I want to build it up here so you can see there's no magic going on. There's no like special sauce. This is it. This is the bare metal. And this plastic piece here it's a breadboard, and it's used for prototyping. So it's got all these little holes. Each hole is a connector, and there's a certain way that these connectors conduct electricity. So they conduct in these rows across the board on each side. So I can put in this microcontroller, and I have access to all of its pins through these conductors on this side and on that side. And then on the far edges of the board, we have the power rails. So this is the pinout for our microcontroller. It has 6 I/O pins that we can use for interesting applications. And you can see each one of these I/O pins is overloaded with multiple functionality. You also see it has what looks like SPI, if you're familiar with the SPI interface. It's a fast-ish serial protocol for accessing memories and programming microcontrollers. So this doesn't actually have a SPI peripheral on it. It is programmed as a SPI device. In fact, it doesn't have a serial interface on it. It doesn't have many different kinds of things that we would like. And it doesn't have hardware for driving the digital LEDs. So we get to write that in assembly. OK, so I need to hook this up. And the very first thing, besides having the microcontroller in there, is this debug header. And so this debug header is going to allow me to program the microcontroller over its SPI interface. And if I had it configured for the serial debug interface, I could also actually do live debugging on it with GDB, insert breakpoints, et cetera. But that is actually a real hassle to set up here. So, alrighty, let's see if I remember how to do this. I don't. I have notes. So we have to connect the programmer up to our power supply. And the reason it needs that is so it knows what logic high is. So what does a 1 look like? And in our case, a 1 looks like 5 volts. And it also needs to know what ground looks like. So we have to have a common ground. So I just plugged it in over to the voltage and the ground over there. And now I'm going to hook up the programming pins. So this is for the reset. While we're programming the microcontroller, we can't have it trying to execute any code or do something. So we're going to put it into reset while it gets programmed. And then we need to hook up the data lines, which I spent about 2 hours trying to figure out the right way to do this last week, which was exciting. So luckily, we don't have to refigure that out today, unless I do it wrong. But that's what the logic analyzer is for. So I have this little board, this wooden board up here that everything's mounted on, and I have a logic analyzer. So we can take a look and see the actual signals that we are using to communicate with the microcontroller and using to communicate with the LEDs. We need power. OK, where are we going to get power? Well, everybody's favorite power connector, USB, is available, and it's quite nice. So we're going to hook up ground. Ground is going to go there-ish. That's probably good enough. I was inspired by Ben Eder, who has a series of YouTube videos. And on his YouTube videos, he builds an entire CPU and computer using discrete logic chips. So he doesn't even use a microcontroller. He uses discrete logic chips, which is super awesome. And it took like, 12 breadboards to do that one. I didn't do it, but I liked watching his videos.
He sells it.
What's that?
He sells it.
Yeah.
You can buy it.
Yeah, he does. And you know what? I did this backwards, and that would have shorted it out. So, yeah, so this is a little bit tricky because it covers the thing. So that's 5 volts, 5 volts, and that's ground. I have no spares. I did not plan well. Okay, that's good. It's good. The lights are still on.
I was going to say, you didn't let the magic smoke out?
No. The programmer did get hot a few times. It's not supposed to. Okay. So, yeah, we're going to plug in the LED too. So, this LED is it's a digital programmable LED. So, it actually has 3 different LED die. They're just these tiny little things. And then it has a digital logic die. It has 4 of these little things packaged in this plastic case. And instead of having 3 separate wires for red, green, and blue, it has a digital in and a digital out. So we're not going to do it today because this microcontroller is really limited. It can drive multiple of these, but if you want to drive multiple of these, it doesn't do a good job of anything else. So we had to give that up. Okay, that'll do. And I'm going to plug in its data to pin number 3. There you are, pin number 3. They don't move. It's always in the same place. Okay. And then, of course, the LED also needs to be connected to power. Let me make sure I do this right. This actually might light up the second it's plugged in because it won't have programmed any value to display. So it loses all of its memory. So after we do that, we're going to want to program this shortly so it's not so bright. And this should turn on now. Let's find out. There we go. Okay, cool. So that's good. Okay, no magic smoke. The light is on. A bunch of lights are on. It's good. Okay, great. Now, we want to actually do something useful with this. And actually, what would help, we have this programming connector. It'd help if I plugged in the programmer. There we go. Okay. So this goes to a USB programmer, which knows how to talk to the microcontroller to program it. So we want to just test and make sure that this works. And once we do that, then we're going to look at some interesting code. Okay, so let's do, so AVR dude is the programmer. I don't know why, but I like it. Atmel ISP. So that's the programmer I'm using plus the method. So ISP in circuit programming. And I'm going to tell I'm using a 8tiny13A. And if this works, then our microcontroller, oh, well, shit, that's not good. Okay. Let's see here. We have this guy, and we have, I'm going to show you guys so you can see this. This is why we test things. If you look at the microcontroller, I hooked up the programming lines, and I hooked up the data line to the LED, but there are no connections to power.
Power ground.
Yeah, so we kind of need that, don't we? I only have an hour and 15 minutes left. We'll be fine. Okay, so still no smoke. There's ground. This is like the worst part for me. Okay, that's probably supposed to do that.
What? Wait. Let me see that again. Okay? Can I see that picture again? Are you off by one on the ground line?
It's kind of at an angle.
Okay.
No, it's on by one. It's good.
Okay.
It's all good. Okay, let's try this again. Yay! Okay, so it's probably the right thing, according to AVR dude. That's great. Okay, awesome. Thank goodness. And the reason the LED turned off, it's actually because there's an old program running on it that turns off the LED. Okay, so the next thing that we want to do is to blink this LED. And that's actually a lot trickier than it should be. So there's like another name for these LEDs. I can see it there. There we go. They're also called neopixels or WS, let's see here, WS2812 plus. I can't believe I didn't remember that. We're running on a 9.6 megahertz clock. And the data rate that these operate at is somewhere around 1 megahertz. And it's actually really sensitive to the timing. It's a serial interface. And so the LED itself recovers the clock from every clock edge. And so the edges of your data line have to be aligned just right so that it can do this. And so we can't do it in C++, unfortunately. But we can do it with C++ and assembly. And I'm not going to go through this assembly too much because I don't think anybody here will ever use AVR assembly. But the fun part is we can use inline assembly and reference all of the same variables. And so if we look up at the beginning here, we are getting an auto attribute, which is for the pin. So that's some data structure, some type that describes the pin that we want to connect to. And the cool thing about that is that pin has information about what address do we need to use to access it, what I/O register do we have to write to, and then which bit within that register does this pin correspond to. And we can convert that to the port number. And we don't get to access just one pin at a time. We actually access a whole 8-bit register. And so if we don't want to modify the values of these other pins, we have to do a read modify write. So that's kind of what we're doing here. We're finding what the previous value is. We're masking it out. And then we're saving that. OK, this is the value to use for high, and that's the value for low. The cool thing here is that we get to use some template metaprogramming, well, just template programming with constexpr for some of these things. And we can use those values in the assembly. And I just want to show you a little bit. All of this is the whole routine. This is pretty much it, plus that. And so we pass in a range, and we can get the first and last pointer to that range. And we use that within the assembly to load each additional byte and drive that byte out that pin. This is the first of 2 times we're going to look at assembly. The nice thing is that we can combine the assembly with template metaprogramming to make things a bit easier and reusable. OK, the first thing that we want to do, though, is blink our LED. And so we have some code here already. And there's a few things I want to say about it, because this should not look like anything that you would see in Arduino or some other microcontroller development environment. I'm using the CIB library, and that's a library we created at Intel for our firmware, and it stands for compile time, initialization, and build. And the whole concept is that we can register features and functionality with services at compile time. We don't have to dynamically allocate memory for it. We don't have to register function pointers. There's a lot of really nice optimizations that we can do using this. And so we have a really simple example here. We have this blinky LED action, and it's going to set the LED RGB values to this, which is going to be purplish. Wait 1 second, and then set it to nothing, and then wait another second. So that's not too complicated. More interesting part is this config. So this configuration right here is part of the CIB library. And so this is where we're telling the library, OK, I want to pull in this LED component, and I want to extend the CIB main loop with our blinky LED. So every time the main loop goes through an iteration, it's going to execute our code here, as long as I plugged everything in correctly. OK, so let's build Blinky. We're also going to play a game on how much memory are we using. And there's a nice tool called Bloaty McBloatface. So we have 186 bytes that we're using. We've got 840 left, so that's not bad. OK, so let's program Blinky. Right? No, yeah. OK, cool. So I can see it's working, but you guys can't. Haha. There we go. We have a blinky light.
Woo!
Yeah, this is, thank you. Thank you. And that's it, that's the talk. Okay. So Blinky's fun. We had lots of crazy assembly just to drive this darn light and to make it do this. What does that actually look like? And so the first thing I want to do is show the analog waveform. And I'm probably just going to do this once because it's kind of finicky. So I'm going to connect my oscilloscope to ground, so it has a reference voltage. And then I'm connecting the probe to the data in of the LED. So we should be able to see what we are saying to that LED. We should be able to. Let's find out. Okay, and this needs to have the right setting on it. This 10x, okay, that's good. And if this doesn't work, we'll move on to the digital logic analyzer, which is nicer anyways. 10x, okay. So, where are we? Okay, well, you know what? It basically looks like this, but a little bit taller. So I think this is going to be a little bit too noisy. Okay, so we're going to move over to the logic analyzer, which is much more useful for this anyways. The point is, I did want to show we don't have nice square waves, actually, on these interfaces. Even this is at 1 megahertz. It's not that fast. Maybe it's like actually 2. But we don't have nice square waves, and what we do have are these mushy sort of rounded off waves where things are just not so clean. But when we look at a logic analyzer, the logic analyzer only knows, on or off. So it's a little bit deceptive. That's fine. Okay, so I am going to tell it to trigger on a logic edge, and we're going to start capturing some data here. We're going to start capturing some data if I plug it into the right one. There we go. It was plugged into ground, so that won't do anything. Okay, here we go. So there's a few nice things about the logic analyzer. One of the really nice things is it has a bunch of built-in decoders. And I know this is probably way too small for you guys to see. But this is a decoder for this protocol that the LED uses. And so you see these nice, square waves. That's pretty cool. This is approximately 1 megahertz, a little bit less. And it's showing that we're sending an RGB value of all zeros. So that's when the LED is off. So if we move over 1 second, which is way the heck, geez Louise, where is it? There it is. And then we zoom way back in. I know there's a better way to do this. This is when we're turning it on. So let's just verify. We're sending it 505. We should see 505 here. And yes, we see 05, 000, 05. And if you can squint a little bit, you might see these locations where we're sending ones, the spacing has changed. And so it's actually the location of the falling edge. So however long it's asserted for, that determines whether it's a 1 or a 0. Okay, cool. So we can blink an LED. Cool. Yeah, again, this is the compile time init build library. This is up on GitHub. We are actively developing it. You can join in if you want and do pull requests or comment on my pull requests. Ben's way better than me. So I mentioned this concept of services and features just a little bit. But these are like kind of keywords that we use when I talk about CID and how it works. And so we have a few services. On the left-hand side, that we're going to see later in some code, a service is something that you can extend, right? We're basically doing dependency inversion, right? I don't want the AVR pin change interrupt to have to know about my code, right? I don't want it to depend on my code. That's kind of crazy. I don't want the CIB main loop to depend on my code as a source code dependency. And this is kind of a toy example, but if you think about large code bases, you can have sort of this core. And this core is your foundation. And you can add features to that core. You really want your features to depend on your core and your more stable parts. And so on the right, we have our features. And then we have our project config. And our project config knows about everything that we're pulling into a particular project. And then we use our CIB library. It has this top, and then it has this magical nexus. I like nexus. One, because of Protoss from StarCraft. But two, because it actually is the right meaning. It's the combination of all of these coming together. And it does some interesting things with that. So our features and our services aren't off by themselves. They're actually packaged up in components. CIB top is kind of like our main, it's like our entry point, and it has some initialization services and a main loop. So we can hook in different functionality at different points. And then our AVR project has interrupts. So when our pin changes, I can register, execute this function. We're going to implement this IR receiver. And by implement, I mean I'll open it up in Vim. We already have the NeoPixel, this light controller, an IR light controller. And so if we look at the direction of dependencies, we're all going from kind of our business logic or application logic, which is less stable and changes more often, and we're depending on things that are more stable and change much less. And then these components can also just call each other directly without having to use CIB. If anything sounds crazy or doesn't make sense, please feel free to interrupt me. There's also a video on this, so that goes in way more depth. This was presented last year at EMBO++. It's a bit more abstract. So I've been talking about services as a kind of abstract concept, but there's specific types of services that we can have. We can have a flow. And a flow could be a long sequence of events that we have to execute, like powering on an airplane or turning on a chipset. There's lots of steps that have to be executed. And depending on what you have installed, there can be certain steps required for those features, for those components. Callback is, instead of like putting function pointers into an array, we can have this simple callback service. And then we can have this indexed message handler, or just a regular message handler. I'll talk about that a bit more. Very sad, the message handler and interrupt manager did not fit on the @tiny. So I'm hoping it's just a bug that I have in my code, because I really intended it for it to be able to fit on small things like this. Okay. So yeah, the FlowService allows us to combine routines, actions from disparate component features. And the really interesting thing about it is that we can create dependency requirements between these different steps. So I can say, before my action is executed, this other thing that I depend on has to happen first. And we actually have this example. So we have a really, really simple one. We have our NeoPixel, which needs to initialize the digital pin on the microcontroller. It needs to set it to an output so we can use it. And then we have this light controller. And the light controller wants to turn on the light to the default value, but it can't do that until the pin is set up. So during our compile time initialization and registration process, our component features are added to this runtime init service. And then our project config says, hey, we actually need to order these so that the light controller happens after the NeoPixel initialization. And so we've overloaded this right shift operator for these actions to say, this is the order in which these must happen. It's a very simple example. In the end, what happens, instead of calling functions through function pointers, the library with the compiler is able to inline everything into a single function. And so we don't have any overhead for this. And this works with hundreds and hundreds of steps, like across dozens of different components. This is what we use. The left-hand side is all compile time, and the right-hand side is the runtime implementation. So the only thing the microcontroller ever sees is the runtime version. And in that same CIB video, I have another example of a flow that's a little bit more interesting. This was for powering on an airplane. Yeah, okay, let's look at this. So this is why I say Ben is great, because he took my flow code, which it has to figure out what's the order of events. So we have to use some kind of algorithm. So we use a topological sort. And it's interesting. So let's take a look. Nope, not there. Nope, not again.
You didn't say you were going to show my code.
Yeah, it's too late. It's already on the internet.
It is.
So this topological sort happens at compile time. Let's just see if I can find a nice representation of what's going on here. Yeah, okay. So this is a nice little bit of our syntax. When we specify like the dependencies between actions or just a list of actions that need to execute, we just do it like this. And another module or another component can say, hey, I need to happen after this and before that. And it gets handled really nicely. Okay, so if you look at, what was the name of this actual function? Do you remember the
Kahn's algorithm.
Kahn's, yeah.
Thinking? Yeah.
Yeah, Kahn's algorithm. It's up on Wikipedia. It explains how it works. It's got nice pseudocode, which is why this code works. But it just goes through and figures out, okay, what's the next thing I can execute? Like, what's the next thing that has no dependencies? And then it takes that off and takes off everything that it was pointing to. And then what's the next thing that I can do? So, yeah, it's nice. Okay, so what all of our customers want is an LED that can log. They all want an LED that can log what it's doing so they can be sure that when it says it is this shade of purple, that it actually is. So in order to do that, we need my notes and to actually connect up to this. I know everybody thinks USB is just for power, but I can actually use this for transmitting data. So that's kind of a hot tip here. And just like there's no hardware for sending digital signals to, sending digital signals to the LED, there's also no hardware for sending serial data. So again, we have an assembly routine for it. I'm not going to show the assembly routine unless you guys really want to see it. I don't think you do. Okay, so make sure I'm connecting this stuff up to the right place. And yep. I also want to see the actual data that we're going to send out. And so I only have 1,000 bytes or so of program memory, and every string that I put onto this microcontroller would consume like more than its fair share of memory. So we need a better way to do logging than just, it looks like a mess, than just using strings. And luckily, we have a library for that. And I will show you in a moment. And it's in CIB, surprise, surprise. So in our firmware, we also, like in our production firmware, we need to log. And we want to log as much as we possibly can because it helps us debug. And we have whole teams of Val engineers, and we don't want them to have to step through O3 optimized, C++20 template code. It's not great. It's not great for debugging. Oh, this signal didn't assert. Why didn't that happen? Well, let's look at this assembly. So here's our Bleaky log, and yeah, let's add a useful log message. Actually, let's do this. Oh, Ben's lightning talk. Oh, I did this one. I love deleting things. Ben's lightning talk has a really nice pattern for. I like the way that you said it, injecting dependencies from the bottom up. So like a low-level thing. And so we need to tell the UART logger which pin to use. I'm using a macro. It's terrible. I need to use Ben's pattern for this instead. But I'm not going to do that now.
Good choice.
Yeah, you're welcome. I am going to add a log message. There we go. See, it's more exciting this way. Okay. Actually, I need to also add the other component. So our UART logger needs to do some initialization. So let's add it. I am so grateful to my past self. Thank you. Okay, let's build this. We're going to build it, and then we're going to see a few things. We're going to see how much memory are we using now, and what does this data actually look like? Okay, so that's 100 additional bytes. Not too bad. It's not too bad. It's not too bad, but you know what? Later on, I've added one log message, and it added another 100 bytes, and I don't know why. So let's program this. We're going to program this, and then we're also going to look at the log data that's coming back. And we're going to do that in two different ways. So we're going to program, and then we're going to show the log. Let's see if you work. Thank you. Ah, okay. Cool. Okay. So it works. We see it's actually turning the thing on and off. And we can take a quick look. Oh, thank you. Yeah. This is magic. Okay. Let's capture another waveform. And
Question.
yeah.
Where is the timestamp coming?
Oh, the timestamp? Well, it's coming from a hack that I added a couple hours ago. It's the system time. It's my laptop's time. Yeah. And so what's actually happening, I'm not storing strings on the device at all. What I'm doing is, well, it's better if I show you. I'm doing something terrible. But it's really useful, and multiple people have invented this independently. So this file is called undef symbols. And the reason why it's called undef symbols is because I compile everything, and I commit this sin of having an extern template function. And I do that on purpose because I want to get the type of my log message, because my log message is encoding its value in the type. And so I can figure out what my log messages are by looking at all of the undefined symbols. And this is terrible to look at, so we're not going to do that. We're going to look at strings.cpp instead, which also, gosh, looks terrible. But you can see, oh, we have a nice little comment. This is off, and this is a function that returns the value of 0. So that's the ID. Turning the LED on, it returns 1. That's the ID of that log message. And at the same time, we generate this JSON file. And this JSON file is what our script actually uses to decode the log messages.
Yeah, I had been wondering for like a device this tiny, essentially, like, you know, does the logging become like a significant bottleneck? Because you had mentioned the fact that you really want to add a lot of logging for these devices. So this thing's really just sending back an identifier every single time. It's just like one number essentially, and then it gets expanded locally.
Yeah,
Okay.
it's doing that. I can actually send formatted strings as well. So I can format, well, I think I talk about this in a moment in a slide. It's very powerful. We looked at no, we didn't, because I got distracted. Let's see here. Let's see if we can find our UART, or, no, that should be right there. Okay, let's try that again. There we go. No. Okay. Well, this wire is terrible. Sometimes these things do not work the way we want them to. The other nice thing, so UARTs can be a bit faster than you would expect them to be able to go. And this one is running at almost 1 megahertz, which is just about as fast as this transceiver can handle. But the logic analyzer should have no problem with it. There we go. Okay, so that was a bad wire. Oh yeah, so that's very exciting. One of the log messages was all 0, so okay. Okay, I think we get the idea. We can send log messages and they're digital. Okay, the speed of your logging and the efficiency, so not taking up a lot of program space and being able to do it very quickly, is really important. And it kind of might seem silly. It's like, well, you're just sending text message, or you're just like literally sending out an ID with some optional payload. It adds up, right? Like if you do a lot of logging, it could easily consume half of your execution time or more, right? And so there's a lot of motivation to make it very fast. And so much so, like if you have hardware accelerated means of getting this information out, use it or make it. And we can make our own silicon, so that's what we do. Cool thing about this library is if we have compile time values, we can actually format those into strings. So we can format values into strings, and we can also concatenate strings together. So we can construct some very interesting things that help us debug and get that automatically. So you can use CIB, register messages, define what a message looks like, and then you can automatically get debug strings for those. You can get a debug string, oh, this message is unknown, like I don't have any handler for it. This is why it doesn't match any of the existing callbacks for it. Runtime values are formatted on the debug host. And we'll see that in a moment. So I did a talk last year on the logging, so you can go to the YouTube video to see it. But basically, I split the build into 2 parts. One part is everything but strings.cpp, and that has the missing symbols. And then I go and extract them. I generate the necessary collateral, generate strings.cpp, link them together, and then we have our full image. And with LTO, it all gets inlined. Like there's no function calls to get the ID. It's just a literal value. Yeah, I'm going to show you the logging script real quick because it is so simple. Yeah, it should pretty much fit on this screen. Yep, that's it. So all we do is we look in the catalog, we get by ID, we accumulate any additional parameters, and then we do the formatting. Okay. And again, this is in the CIB library. So not the serial logging part, but this framework and string constant for doing this logging. So now we want to add our remote control. And This is when it gets a little bit more interesting. So we have this remote control from AliExpress for like $1. And it's got all kinds of nice colors, so that really caught my attention. We want to be able to do on-off control, and then we want to be able to change the color of our LED. So let's go through and add our receiver. So this little guy right here is an IR receiver, and it does a little bit more than you'd expect. When an IR remote sends a signal, it is actually modulated at 38 kilohertz or so. So 38 kilohertz is the carrier wave, and then it does bursts of that to send the digital logic signals. And so that little IR receiver takes care of that for us. So let's hook this up to power while it's all plugged in. That's totally good. And ground. And again, there's no hardware for decoding these messages. So we need to do this in our C code. Luckily, this is way, way, way slower than any of the other interfaces. So it is a lot easier, and we don't actually have to do assembly. There we go. Okay. Well, let's see if this works. So we're going to connect this one to our logic analyzer as well. And get all these little guys connected up. And this is going to go there too. And so we'll actually be able to see the codes. And there's a decoder for this protocol as well, which is nice. Okay. Let's go here. And we don't have to do anything for this to work. It should just be able to see our messages. So I'm just spamming buttons. I don't know. There we go. Okay. We can zoom out a little bit. And this is way, way, way slower. Later on, we're going to see how much slower it is. But basically, we have this lead-in, which kind of tunes the receiver's gain control. And then there's an address. There's an inverted address, a command, and an inverted command. So the inverted versions of these help us do some very, very basic checking that is good for a cheap 8-bit microcontroller. But I'm not going to do checking. We got our waveform. So now this is input, and we don't know when we're going to get this. So we need to use an interrupt, and we need to have the microcontroller execute some code when this pin changes. And so the AVR has this exact feature that we want built into it, and we can use it. The thing is, interrupts are not a part of C++. C++ doesn't talk about it at all. So let's take a look and see what we need to do here. We're going to use the CIB library still. And this is the code we want to execute to initialize a few things. We have to make sure, okay, interrupts are on. The interrupt for this pin is enabled. The pin change interrupts in general are enabled. The pin's it's an input pin. And then we also want to change our timer and enable it so that we can count how long has it been since the last toggle on that pin. And then we have this IRQ. And so every time we get a pin toggle, we're going to log out a message. And this is where we're going to see how hilariously slow that protocol is. And the nice thing is, I can actually log out how long has it been. So I've never decoded this protocol before. I really don't know how. But this was a great help in being able to do that. Here's our PC int 0. This is our AVR pin change interrupt. I don't have to know about it. I don't have to know how to do that. It's really weird. I had to look it up. It was a real pain to get that set up. And I can show you we have this AVR main, which does that for us. And here we go. So on every microcontroller, they have their own way of doing it, and depending on which compiler you're using it, they have their own way of doing that. On AVR GCC, it's this attribute signal, and then you have to have the correct name for each one. So what we're doing is we're just hooking up that service, and we're going to call that service whenever that interrupt gets triggered. This is a nice low-level abstraction for us to be able to use. So let's build IRQ, and let's see how much space we're going to use. It shouldn't be bad because we're not doing the LED in this one. Yeah, 282. Okay, so let's program this and take a look at the log. Let's see if it works. Yay! Okay, it works. This is actually useful. So every time our pin toggles, we're getting a log message. And if I had to log the whole string, I don't think I would be able to do that fast enough to keep up with all of these messages coming in. But if we use the logging library, we can get that. And so this train of, this square wave down here is the IR signal. And all of these different lines, it's the entire log message. And so it's just a completely different order of magnitude. And it's just 2 bytes for the log message. So using this information, I was able to figure out, okay, what are the rules for this protocol? How does it work? And I could write something that can actually decode these packets so that we can use it. Okay. Yeah, and let's actually do that now. So we can just skip ahead in time and take a look at IR LED. Okay. And so this is starting to get a little bit more complicated. We have our NeoPixel LED. We have this Neo light controller, which is like a generic light controller, turn on, turn off, set color, that kind of stuff, toggle. And then we have this IR light controller. And this IR light controller, that's the new part that understands this is a message, and how do I convert that message into actions for my LED? Yeah, okay. So we're adding all of these components, and then this is that little bit I talked about earlier when I was talking about flows. Now that we have these 2 components together, we need to make sure that we initialize the digital wire, the digital pin, before we try to send any data. So we got that. Okay, now let's give this a run. We're going to build it. I'm going to look at one more thing, actually, because IR light controller. Yeah, okay. So this is just using a basic callback. You can kind of think of it like, oh, I'm registering a function pointer, but it's at compile time and it's faster. These are the different commands that I discovered that kind of look like, yeah, that probably turns it red. That probably turns it on and off. And so for each one of these different commands, I'm just calling the light controller. So we can set to specific colors, we can increment it, we can decrement it, so we can pick specific colors. And if we get something that we don't understand, we can just print that out and let us know, hey, we don't know what that is. But check this out. I don't have to, like the IR receiver logic doesn't have to directly understand the LED, the IR light controller. It doesn't know anything about it. Instead, my IR light controller, which needs to get, it has this real true dependency on this IR interface, depends on that. So our dependencies are going in the right direction. Okay, let's see how big this is. Okay, this is the magic number right there. We have 1,024 bytes. I have 16 bytes left, and it's scary. Down here, I'm using 4 bytes of initialized data and 9 bytes of zeroed out data. And that's just in memory. It doesn't use program space for the zeroed out stuff. Okay, so let's program this, and we are going to also show the log. Sometimes it fails to program, so that's fun. Let's see. Well, that's fun. Okay, cool. So AVR do did not let us down. Now let's try it out. So let's turn it on. There we go. We're getting our log message. Let's set it to different colors. Yeah, and we're getting log messages, and they're actually saying exactly what colors we're setting it to. Let's make this a little bit smaller. There we go. And I want to show you guys this as well, because it's just so cool. Okay, so there we go. We can turn it on and off. There's our LED, red, green, blue. This is like the most important part. This is the most important takeaway of this whole talk right here. Anyways, it works. And yeah, thank you. It works, and we can get interesting, useful log messages if you want to know what the exact color is. Okay. So this callback service, that's what I use to get the messages. It's very simple. You can't control the ordering of things. And it's easy for the compiler to inline everything. And the callback service itself doesn't add any additional logging. So it doesn't really know what you're using it for. It's a nice and simple thing that can be used for many different things. We're not going to look at that. Now, what I really wanted to use was the message handler service. And the message handler service is perfect for this kind of application. And what you can do is you can define what your messages look like. And you create a template instantiation that describes, this is the message, these are the fields, this is how you decode the fields, these are the types of the fields, these are the names of the fields. And so with that information, we can actually log, this is a message that I got and I don't know what to do with it. We can also define, this is a special command message. And so the command opcode must be this value. And so we get some actual type safety there as well when we receive messages. This is a really cool thing. The framework understands the message structure, it understands the fields. We can then create callback predicates that can put requirements on these fields. So a message comes in, we need to figure out where does that message go to? Which component wants to process, or which components want to process this? Having that knowledge gives us a lot of power to add more capabilities. And one of them is debug. Why did this message not get handled? It'll tell you exactly why. Because it didn't match this predicate right here. It was a 5, but the predicate wanted 6. It also gives us some really cool opportunities to optimize the algorithm that we use. And this is a negative cost abstraction. And that's not even like an exaggeration. But for the message handler framework, Michael had a great talk last year on it. It's up on YouTube. And again, message handler is up on the CIB repo. So there's this indexed version of the message handler service. And this indexed version takes advantage of the fact that we know what the requirements are at compile time for each one of these fields. And so we can build an index for each one of them. And we can also construct the most efficient lookup method, either a direct array lookup, a linear search, a hash, and we can pick the optimal hash function for it, all in compile time. And then we can dispatch our messages in constant time. This is important for us. There's a whole algorithm for it. I'm not going to talk about it here, but it's cool. It's fun. I did benchmarks on real hardware. This is running at 400 megahertz. The x-axis is the performance that we have with our index one, and then the blue line is how many nanoseconds it takes doing the naive evaluation of every predicate individually. So on this particular hardware at 400 megahertz in-order CPU, we can look up message callbacks at 145 nanoseconds, which is extremely helpful for us.
Is the blue line, is that what Michael Case presented, the previous version?
That's the previous version that just does a generic lookup. This is with 150 callbacks, and they all have their own predicates. So the initial implementation is just look at each one and evaluate it.
So
right?
this displaces some of what was from last year.
No. It's the exact same API. Right, so it's just under the hood, we can change this to add this performance. Yeah, it doesn't really invalidate any of it. I gave a talk on this at EMBO++ earlier this year. If you're interested in it, if you need to do any kind of message dispatch in your firmware or in other applications, I highly recommend to watch that. And of course, this is, there's a pull request up on CIB for it. So we were able to do a whole lot of really cool things, culminating in the amazing ability to turn an LED on and off. But we can use the full power of modern C++ in embedded systems. There's a lot of very powerful abstractions that improve safety, that improve performance, and improve developer productivity, and they can all apply to embedded systems down to having 1,000 bytes of program memory and 64 bytes of data memory. So there's really no reason not to be using C++ on these embedded systems if you're using C code today. Looking forward, we're continuing to develop the CIB library. We have more libraries that we're working on, like safe arithmetic, which is a work in progress. It's a work in progress, so it's warts and all. It's being developed in the open. I use this config register library. You might have seen like apply read and apply write in my code. I didn't talk about it. It's an internal library that we have, but some version of that will likely be opened up. But yeah, there's a lot of really cool, exciting stuff in embedded with C++. So I hope we get more embedded developers, and I hope we get more people doing cool things. Thank you, everyone.
One question I had, and by the way, it was an amazing talk. I would say one of the boldest live demos that I've seen.
Thank you.
But one thing I was curious about, so in the beginning where we needed that like handwritten assembly routine,
Yeah.
is that specifically because like the timing requirements are so tight that
Yeah.
you need it to line up on exact clocks, or
Yep.
like
It has to line up on the exact clock,
okay.
and
we just can't get the compiler to understand.
you cannot. The compiler won't do that for you.
Okay.
It doesn't care.
Yeah, gotcha.
It has to be fast, and it has to be very precise. If the edges don't line up just right, then the receiver won't be able to recover the clock and data.
Okay.
Yeah.
Would it have been possible to replace the assembly with intrinsics?
Maybe. I didn't bother because if you do intrinsics, the other thing that might happen is the compiler, it might move things around. I'm not sure. For me, it was easier to just go straight into the inline assembly and then not have to worry about that. Yeah. It would be really cool, though. It would be very cool if there was like a C++ library for like building these kinds of timing critical things. So then you don't have to do the assembly, and you could port it from one platform to another.
So I'm not in the embedded space. This might be a dumb question, but can you clarify again why you couldn't have used C++ in that situation, and you had to use?
Oh, for the assembly? Yeah. Let's just take a look, and I can show you. It's we're gonna look at the UART code. So this is the no, that's not what I wanted. That's silly. Yeah. Okay, so the UART code is going to look similar. In fact, it's probably going to look exactly the same as the NodePixel data, but I promise this is different. We have to very precisely count the number of instructions between asserting or deasserting the signal. And we need to make sure that the period, like the length of each one of these bits, is exactly the same. And not only does it have to be exactly the same, it has to be the exact correct amount so that we match 921.6 kilobits per second. Yeah, and it's funny. I just remembered why I did this. I was looking at this code last night, and I was like, why do I have an even bit and an odd bit? And the reason why I'm treating even bits and odd bits differently is because I can't get that timing with the whole number of instructions, right? And so my even bit is like one extra clock cycle than my odd bit, so that over the course of 1 byte, it's staying in line with the correct bit rate. And that kind of variance is okay for the receivers to be able to deal with. If I use C code, or C++, or any language other than assembly for it, there's nothing in the language that lets you specify the timing of instructions at that granularity. If I had a 400 megahertz processor, I could do it, right? Because I would just wait, right, the correct number of microseconds. This micro can't do that. Yeah.
Can you elaborate better on, there is a part that probably I didn't fully grasp. I understand that, of course, you end up sending out in logging as an encoding.
Uh-huh.
But I don't understand how you then, let's see, where that does the mapping back to the string that you encoded, right?
Oh, yeah.
So you have a script that there must be another piece of code on your laptop that does it, or?
So there's a few different parts. There's this one script called gen UART logger catalog. So it's, again, a very clever name. That basically looks at the undef symbols file here that has the undefined symbols. It has the full type name information in there, right?
But
so
then that's on your laptop.
Yeah, it's on my laptop, yeah.
Okay, yeah, that's something that I was like, well, must be some counterpart that does that, right?
Yeah, I think I went through it pretty quick. I generate this strings.json.
No, I saw that, but I still didn't understand where it was, because from the way you ran it, it seemed like that it was immediately being read from the serial connection on your AVR dude.
Yeah.
So I didn't see any process that was feeding.
Yeah, so I'm running this build command, and this build command is a dirty hack.
Okay.
It's not CMake, it's not make, it's just this shell script. And try not to look at it too much. But I do want to show you the interesting part. So GCC NM, this is where I'm getting the undefined symbol. So this is where I'm getting the log message definitions, like what log messages are there. And then after that, I call Python, and I call my script that extracts that log message information. And it generates the strings.cpp, strings.json, etc. And then I call GCC again. In my normal production flow, I create a static library, and then I compile it and link it with strings.cpp. For this, for some reason, that didn't work. I don't know why. I didn't want to debug it, so I just go through the whole build all over again with strings.cpp added.
So just to follow up. Basically, that doesn't mean that in practice you are deploying a partially linked object on your microcontroller, because it has undefined symbols, right? It's
yeah. So this command, the second time I run GCC, I am including strings.cpp, which includes the definitions. So so halfway through the build process, I create the missing symbols.
Okay.
And then I finish compilation.
Yeah, but that doesn't end up in the code that you deploy in the microcontroller, right? That's the point.
Yeah. Yeah, strings.cpp ends up on there, but the string data doesn't.
Okay.
So I was going to say, maybe if I could just restate. So the idea here is that you have these external templates that are unimplemented in the initial build. You can extract the string from the actual symbol name that gets wrangled in. You then use that to basically dynamically decide, okay, so I have this many strings, so this string is ID 0, this string is ID 1. You then code gen that, so the implementation is just like return 0, return 1, whatever. And then on the local side, you use the JSON here to actually decode what was that thing. And one other thing I'm curious about, so for the interpolation, I assume that comes through, you said it was like a secondary byte or something that actually passes the value that gets interpolated.
Yeah.
Is there a maximum number of interpolations you can actually accomplish? Or like, is there like a bandwidth limit there?
It depends on how much memory you have.
Oh, okay. That makes sense.
Yeah.
Doesn't everything?
Yeah.
Yeah.
I basically just meant, is there like a practical limit that you run into? Or
Something less than 1024.
Okay.
We
So
also use the MIPI protocol in CIB.
yeah, so the CIB
Microcontroller.
library uses the MIPI protocol. I don't know. I didn't see any like built-in limits on the MIPI protocol for that.
okay.
MIPI protocol is also like 32 bits, and it's got bigger headers, and it's not suitable for this. But it's what we actually use.
Yeah, it's a really cool trick. Yeah.
Yeah. I'm not the only person to have done it. I've met 2 other people that have independently developed similar schemes, which is like kind of wild.
So I got a kind of two-parter. So just to make sure I clarify for the second part, for the callback API, is that a callback exclusively for interrupts?
Yeah, it's for whatever you want.
Okay, but that does include interrupts.
Yeah, you could use it for interrupts. That's actually another thing that I'm really sad to have not been able to put in. I have this interrupt manager. It comprehends status bits. It comprehends enable bits. You can define, these are all the interrupts that this system has. And then you can hook into those interrupts as you want. And if you don't use any of the interrupts, they get compiled out. But I think I have a bug somewhere that's causing things to not get inlined. And so it didn't fit.
Okay, and then my other question was, does CIB allow you to like disable interrupts during certain flows or anything like that?
So that's such a good question. We added this dynamic interrupt controller. And it's up in CIB. It should be up there now. Yeah, it should be up there now.
Yeah, it is.
And it lets you basically assign interrupts to different like resources. And then you can say, well, this resource isn't available. And then it turns off all of those interrupts for you. So that you're not going to get an interrupt during that time until you say, okay, this resource is available now. And you can have multiple resources. And then each interrupt can actually depend on multiple resources. And it keeps track of all of that for you.
That's
Yeah.
cool.
Yeah, that was a fun one. There's a lot of template meta programming.
I guess I got a question. I know for some uses of embedded systems between like C and C++, there's like different startup files involved.
Yeah.
Like using G++.
Yeah.
Is it the typical ones that are normally provided for AVR? So I know like ARM's like different. Sometimes
Yeah.
you have to link in your own composable
Um,
constructors if you want to use C++ over C.
Yeah, I didn't look. So Ben laughed because it's kind of a pain. It's a pain setting up like the runtime stuff if you want to do it on your own. For AVR, I just ignored it for this demo because I'm like, I don't want to have to learn that because I have PTSD from doing it at work. It's yeah, I don't have a good answer for it. I don't have a good answer. But what I can say is I don't need to use any C code in any of my runtime initialization. And we do the least amount of assembly needed.
Okay. Thank you.
Yeah.